the EPSRC Future Manufacturing Hub in manufacture using advanced powder processes. We are a group of 6 universities who are working together to solve the problems of use of powders in some of these advanced processes like additive manufacturing and spark plasma sintering, and enable them to meet their potential as full manufacturing solutions for industry.
MAPP is incredibly collaborative. It brings together academics and industrialists from across the UK and indeed worldwide in order to solve a common challenge, advancing the processing of powders. Through the MAPP project, we're studying additive manufacturing, also known as 3D printing. With 3D printing, you melt and then re-solidify material in under a thousandth of a second. Because of that, we really don't understand the phenomena that are occurring. Using diamond light source, the UK synchrotron, which is behind me, we can actually capture the process and look inside of metal objects as they're being formed at 1 million frames a second, giving us unique insights.
I'm working on ceramic materials, so these are the oxides of metals such as aluminum oxide, zirconium oxide, and can be other things like silicon carbide. And these materials have outstanding properties. They have high hardness, high strength. They are resistant in challenging environments such as high temperatures or corrosive conditions, and that's why they are of interest to a lot of people.
So here in Leeds, we are doing the powder characterization and correlate that with the powder flowability and spreadability process. So my focus is on X-ray macrotomography and ball indentation, and then correlate those results with my colleague Dr. Gardy for the spreadability process.
So some of the work we're doing within MAPP is looking at adapting the processing parameters as we build a part. So here we have an SLM part, selective laser melted part, building up layer upon layer. With a conventional process, there is no adaptation or intelligence behind the actual melting, so it doesn't consider the geometry as you build up the part. That is a mistake or something that is not capitalized on fully. By considering the geometry of the component as you build up, you can change the processing parameters and potentially reducing the stress that's developed within the part, which is a common problem within this process.
The work that I'm currently doing on this machine is looking at wear-resistant coatings for rolling and forging applications, but primarily at the moment focusing on characterising the powder that goes into the process. So we have a number of powder hoppers around at the back of the machine where we put our raw materials in. And they flow through and come out through a nozzle where the laser beam is. And it's critical to make sure that the flow of powder into the laser beam is controlled and managed and understood so that we get the melting characteristics right and it builds correctly. And this leads back to really understanding the raw materials that we're putting into the process.
We're here at Jeep Beamline, one of the over 30 beamlines at Diamond Light Source. Each beamline specializes in its own science. This beamline specializes in generating high energy X-rays, so we can do things like look inside of this component, which is a mock-up of a turbine blade, which is being repaired in order to extend its service life. Our group specializes in designing nano-precision instruments that fit on these beamlines to see inside materials during the manufacturer use. This is a rig we designed to perform additive manufacturing, or 3D printing. Using the Jeep beamline, we can see through the metal to reveal the interaction between the laser and powder particles, making the process more efficient and effective.
One of the exciting outputs that we have out of the MAPP project is a very recent application of multi-input control for laser powder bed manufacturing, and we are about to publish this result. It's very exciting because it's the first demonstration of multi-variable control in laser powder manufacturing, and perhaps longer term, where I see quite a lot of impact for projects like MAPP, is the integration of machine learning with real physics that are relevant to a manufacturing process.
So we do a lot of work together with companies in the aerospace sector, the oil and gas sector, and the nuclear sector. They are interested in understanding better how processing parameters affect the performance of the components. And that's again where we need to fully characterize the material to understand not just what the material does, but why it does it.
By working with MAPP, It's bringing together world experts to solve great challenges, and it's bringing together the best people from a range of disciplines, all to solve a common problem of the advanced processing of powders.